Hi, I'm Brandy Heflin. I'm a personalized physics instructor, and I help high school and college students feel confident and successful in learning physics. Welcome to my AP Physics exam preparation video series. Over the next several weeks, I will be releasing sample questions from each of the 4 AP Physics exams so that students can become familiar with the free response section and what kinds of questions will be asked, as well as how the exam will ask them to demonstrate their knowledge. As a tutor working with students all over the country, I know that not every student has the ability or the opportunity to use released exam materials while they're preparing, and this video series is primarily intended for those students. AP Central lists the following types and number of free response questions students can expect to see on the AP Physics C Mechanics exam. One major kind is experimental design, and in fact, this video will be the second one on experimental design that I'm going to show you. And the questions on the whole will assess all 7 of the science practices listed here. Today we'll be looking at the C Mechanics exam, question number 1 from 2016, which covered Newton's laws of motion and kinematics. Mass M is pulled along a level dynamics track as shown above. A force sensor is attached to the cart with a string and used to measure the horizontal force exerted on the cart to the right. A motion sensor is used to measure the acceleration of the cart with the positive direction toward the right. Friction is not negligible. Part A. On the dot below, which represents the cart, draw and label the forces, not components, that act on the cart. Each force must be represented by a distinct arrow starting on and pointing away from the dot. So they've given us a really nice clue there that friction is not negligible. So we know that there's going to be a frictional force, and it's going to be to the left because it's in the opposite direction of the way the cart is moving. And we know there's going to be a tension force to the right. Sorry that that's not quite level, but it is intended to be all along a straight line, not angled. You know, let me fix that actually. We want that to look just a little bit better, be a little bit more clearly horizontal. All right, that's better. And it's going to be longer than friction because we're told the cart is accelerating to the right, so that we know that whatever force is pointing to the right has to be bigger than the sum of all forces pointing to the left. And then, of course, we're going to have a normal force upward, support force from the surface, and a gravitational force downward. So our points, we're going to get a point for, this is all drawing and labeling, a point for tension, a point for labeling the force of friction. Again, this is drawing and labeling. And then we're going to get a point for both of the forces in the vertical direction. And then note, and this is worth, let me write this down. So just a note, you can earn a max of 2 points. If there are any extraneous vectors. A student pulls the force sensor with a constant force, and the cart accelerates. This is repeated for several trials with a different constant force used for each trial. The data are recorded in the table below. B1. On the grid below, plot data points for the acceleration of the cart as a function of the force sensor reading. Clearly scale all axes. Draw a straight line that best represents the data. And of course, I'm going to put this on the next page. So I have plotted this with a tool called Graphical Analysis. It's a free data plotting. I can make that cleaner. Hang on. Easier to read. It is a free plotting and analysis tool from Vernier. And then here is my best fit line. And so here are the points awarded for the graph. We get 1 point for a correct scale that uses more than half the grid. So don't cram all of your plot into the bottom left corner. Spread it out and use as much of the grid as you can. Oops, I actually left out more than. Let's fix that. All right, and then we're going to have a point for correctly plotting the given data. And again, I'm leaving off correctly. It's just one more word to write. And then our final point will be for drawing a straight line. Consistent with the given data. And note that you can earn full credit if the axes are switched. So let me note that. Part 2, using the straight line from the graph, calculate the mass of the cart. So if you think about, there we go, net force equals ma, or acceleration equals 1 over mass times your net force, then it makes sense that we're going to be looking at the slope. So I will show you the slope calculation from the scoring guidelines, although I did use the one from Graphical Analysis. And this gives me 2.16 per kilogram. And it's worth noting that the scoring guidelines state that a linear regression would give 2.12 kilograms per kilogram, sorry. So you do have to plot by hand, but you can also do a linear regression for a scatter plot on your graphing calculator and use the linear regression tools. So now we need to be able to say that the slope is equal to, the slope is equal to 1 over m. So that means that m will be equal to 1 over my slope, and my slope was 2.16. So I'm going to get 0.463 kilograms. And likewise, with a linear regression, you would get a slope of, a mass of 0.472 kilograms. So not that far off. For this part, you're going to get a point for correctly calculating the slope using the best fit straight line. That was actually not well written. Hang on. Let me fix that. And they do have a note here. So we're going to use the best fit straight line and not data points. So you can only use data points to find your slope if they lie on the best fit line. Otherwise, you have to choose points from the best fit line. And then our final point is for correctly calculating the slope. Sorry, correctly calculating the mass using the slope. Let's fix that. And part 3, using the straight line from the graph, determine the magnitude of the force of friction. So you may have noticed that there was an x-intercept, right, when the acceleration was 0. This is actually worth writing down. When the acceleration was 0, there was already some amount of force acting on the cart. So the x-intercept, or I should say when acceleration was 0. Actually, my bad. No, that's correct. That's correct. My brain got confused for a moment there on x versus y-intercept. We're good. There was still a force on the cart. And that makes sense, right? Because that would happen when we've got constant velocity, and the tension force will be equal to the force of friction, which I think we used actually just a lowercase f for that earlier. So let me correct that and be consistent. So yeah, we're going to just look at the x-intercept here. So again, thinking about y equals mx plus b, when the y value of acceleration was 0, I had a slope of 2.121 from my plotting software times x minus 0.5763. I got a value for x, which was 0.272 newtons, and that's going to be equal to my force of friction. The scoring guidelines also just specify that friction equals 0.272 newtons, but they don't show you how to get it. Yeah, so our scoring here is just going to be 1 point for an answer with correct units. Consistent with the x-intercept of the graph. Yeah, of the graph from B part 1. The above experiment is repeated by using a constant force sensor reading of 0.45 newtons. The cart starts from rest at time t equals 0 seconds and is pulled for a time of 2.0 seconds along the dynamics track. C part 1, determine the acceleration of the cart. So my thinking on this is that acceleration will be equal to net force divided by mass. So that's going to be the applied force minus the frictional force divided by the mass. and that gives a value of 0.376 meters per second squared. And if you use the value from the linear regression, it ends up being super close. So linear regression, I got 0.377 meters per second squared. So basically the same thing. And our points here are just for an answer with correct units. Well, the answer. Consistent with B, part B. Either from the graph or calculated using mass and friction. Part 2, the string breaks at time t equals 2 seconds. Calculate the time it takes for the cart to stop after the string breaks. Sorry. So let's think about this for just a moment. What do we have going on? We have, that's a bad cart. Let's fix that, make it a little bit better. So we're going to have our cart is being pulled a span of 2 seconds. I'm actually going to draw that a little bit differently. So our cart is just being pulled and it's going to move. And then, it had an initial velocity of 0 meters per second here. And so it's going to have some V that I'm going to call V1 here. And then the string breaks, and now the cart is going to be coasting to a stop. I can spell coasting, coasting. And then somewhere over here, we're finally going to have, I'll call it V2 equals 0 meters per second again. And so we've got friction only that's going to be slowing our cart down. So we've got a few steps we are going to have to follow. First of all, we need to know how fast is our cart moving when the string breaks. So let's start with that. So 1 will be equal to V naught plus AT. And so we started from rest. We will take the acceleration 0.376 that we just found in a previous part, multiplied by 2 seconds, and I get a V1 equal to 0.752 meters per second, or a V1 rather. And so now we need to think about what happens while we're coasting. Actually, that'll be nice if I'll put that underneath the part where we're coasting. Makes sense. So over here, we're going to have V2 is going to be equal to V1 plus a new acceleration times time. And I guess I really could label like acceleration 1, acceleration 2. So this I'm going to call actually acceleration F for acceleration due to friction. So this acceleration is going to be just due to friction, and we can find it with the frictional force divided by the mass. So we're going to stop at the end, and we know that we had 0.752 was the velocity when the string breaks, and now we can substitute our 0.272 newtons for friction and our 0.463 kilograms for the mass times time, do a little algebra, and we'll get 1.28 seconds. Okay. So, our scoring here, we're going to need a correct equation to solve for the speed of the cart when the string breaks. And there's a little bit more here in this note. With an acceleration consistent from part C1. And then we are going to get a point for recognizing, +1, that the acceleration of the cart after the string breaks is only due to friction. And they want us specifically to do the friction from part B. Because we haven't calculated friction anywhere else, so that makes sense. And then our final point will be for this right here, for using the final velocity before the string breaks. As the initial velocity for the cart stopping. Oh, yes. And we have to use it in a correct equation for time. The experiment and analysis in parts A and B are repeated with a cart that has the same mass but a greater force of friction. Will the slope of your new line be greater than, less than, or equal to the slope of your line in part B1? And we're going to get equal to, because again, we saw that the slope was due to the mass. The mass hasn't changed. And you're going to get a point for selecting equal to. That's supposed to be an arrow. It's not well drawn. Hang on. Hang on. So for selecting equal to. And then, will the horizontal intercept of your new line be greater than, less than, or equal to the horizontal intercept of your line in part B1? Well, we have a greater force of friction. So when our cart has an acceleration of 0, we're going to need a bigger force to be pulling on it. So a bigger pulling force to balance out that frictional force. So that means that we're going to have a greater horizontal intercept, because that horizontal intercept was the force of friction. And our point here is going to be for selecting greater than. So I hope you have found this explanation of another experimental design question from the AP Physics C Mechanics exam helpful. If you have a video solution request for my YouTube channel, you can send it to me at physicsproblemrequests@gmail.com, but I won't be putting anything else up until the AP series is over. If you need some email assistance, you can send your questions to freephysicshelpline@gmail.com with a limit of 10 questions per academic year. If you'd like to know more about my online physics tutoring services, you can email me at brandyheflinphysics@gmail.com. You can visit my website, virtualphysicsofficehours.com, or you can find me on Facebook. I'm Physics Tutor Brandy. So just a few notes. AP is a registered trademark of the College Board. The College Board does not endorse or recognize this video or my services. All of the materials presented are available on AP Central at the link shown here for the AP Physics C Mechanics exam, and those materials include the release free response questions, the scoring guidelines, and sample student responses and commentary. I strongly encourage students to review those sample responses to get a feel for the different levels and quality of the responses prepared by the students who took these release exams live, and to see what the scores for that year were looking for and how they decided to award points. If you have questions, you can reach me at brandyheflinphysics@gmail.com. I'm Physics Tutor Brandy. I love physics, and I love helping you. Until next time.